by Martin from Universality to Variability in the statistics of word frequency using generalized entropies.
Thanks. Yeah, first, thanks a lot to the organizers for putting together the program. It's very interesting so far, and thanks for giving us the chance to present our work. 2 consecutive talks.
Yes, I just
Since all of those results are in collaboration with Eduardo and some other people mentioned here, and it's what I'm going to talk about is essentially continuation of the previous results that were presented. And just to remind you, one aspect relating to universal laws or scaling laws in languages is this law that Eduardo showed, and this is the data from the Google Ngram here, where we found this double power law, which can be interpreted, this cutoff, as this core vocabulary introduced by Ramon. And in fact, if you look at individual years of this rank frequency distribution, this is for the year 1850 or for the year 1900 or 1950, these curves are essentially very indistinguishable. So this, with a remarkable precision, this law holds across all time. So almost whatever corpus we looked at, this seems to be true. But in terms of applications or trying to understand language change, and we know language changes, we could ask, well, what is different between these curves, right? There has to be a difference. We know that there's a difference, and I'll explain that or try to visualize that by taking apart these curves and not look at the individual ranks, but look at individual words. And then we will see that, of course, the word "and" it will more or less stay with the same frequency, the same rank. But if we look for words that are further in the tail, for example, that word genetic, we'll see that from 1850 to 1950, its frequency rose by, or the rank jumped by more than 1 decade. So we know that there is this change. And in the previous years, including us, we tried to quantify. How can we quantify the change exhibited in this, or the variability exhibited in this rank frequency distribution? One thing we did was to look at, even though the core vocabulary, the size of the core vocabulary stays constant, we looked what are the words that are inside that core vocabulary. And what we found is that measuring the overlap of the core vocabulary over time, we found this exponential decay, and then you can look which words were included in 1900 and which words entered in 2000, and let's say in terms of the words that you encounter in newspapers and so on, it makes sense.
Can you explain what is in this plot?
Sorry. So this on the x-axis is the separation of years, and on the y-axis is the fraction of words that are in the core vocabulary in both years. So if it's 1, it means the core vocabulary, the words that are contained in both core vocabularies are the same, and if it's 0, means they're disjunct. And we found that no matter from which year you start and you follow that over time, there's always this characteristic exponential decay.
So
over time.
How do you define the core vocabulary?
The core vocabulary is defined by by this model. The core vocabulary is the is the first approximately 10,000 words from that rank frequency distribution.
Below B. Below B.
Yeah. Yes. And we showed that the size is more or less constant over time. We just looked which words are contained in there. Exactly. Then, in a more rigorous analysis, the group from Peter Dodds, they looked at these, also found this double power law and defined frequency thresholds. So they didn't look at the core vocabulary, but they wanted to check, are these frequency thresholds defined certain frequency thresholds, and they showed that these are constant over time. And they measured the flux of words that go from 1 year to the next that cross these frequency thresholds. And they found that even over time, follows a remarkable pattern, that this frequency flux is constant over time. It is different depending on where you put these thresholds, but then there's a remarkable regularity in that change. And maybe as a third example, I want to mention the work of Bob Garrett and Sir Wichmann from Leipzig, I think, is to measure the difference between the whole vocabulary of different years and measure how, from year to year, how does the whole ensemble of words from the Google Ngram change from year to year. And they found that with some spikes, you have a very constant rate of change from year to year. And what I want to say from that is that even though these universal patterns seem to be, let's say, fulfilled with a remarkable precision, we also have to look at, or the variability also seems to show a very regular pattern in which this change occurs. And from these two observations, it seems that there's a very remarkable, very delicate interplay between the universal aspects of language and the variability aspects of language. So is this issue of coexistence. And what I want to motivate is that we should not look at these two things independently, but that we know these two things are actually interrelated. And
you will quantify the changes?
Excuse me?
You will quantify the changes?
Yes, I will quantify the changes, and I will explain how I will quantify the variability. And at least as far as I'm aware, there have been 2 examples I know where people try to look at, assuming there is some variability in language, how does that affect the scaling laws that we measure? And one example is also from the group of Peter Dodds, and I will not go in the details of this model, but he proposed this model that we mix a bunch of small texts and we generate a big text. And his claim is that that all these individual texts, they fulfill or they show a simple power law, the one that was initially proposed by Zipf. And his claim is that this model actually, the act of mixing introduces these 2 power laws. We can discuss how much this model explains this observation, but I think it's an interesting proposal that the variability from text to text has an influence in the universal law that we will measure. And one aspect which was mentioned by Eduardo is in the example of Heath's law that the topical variability leads to larger fluctuations. So we know that we can connect Zipf's law, where we plot the frequency as a function of the rank, and we can easily connect that to the growth in Heath's law. In the vocabulary growth, it's connecting these 2 exponents. But what we showed, looking at the fluctuations, meaning not just at the average growth, but how much looking for different texts, what is the spread for a fixed value of text length? What is the spread? And if you do this simple model, you would actually predict this square root scaling, but what you see in data is that your fluctuations will scale much with a different exponent, meaning that your fluctuations will be much, much larger. And we proposed the model where we explain that as a result of the topical variability from different texts. And what I want to do in the following is actually go the other way around, is to show what is the influence of universal aspects in how we measure variability. And in particular, that was mentioned in the title, I will show or try to convince you that using generalized entropies actually is very helpful in doing that. And we will try to, or we can actually really see how these universal aspects, especially Zipf's law, affects what we measure in variability. And I will, after explaining these concepts of entropies and generalized entropies, I'll focus on 2 main aspects. One is the aspect of what I call as spectral information, which in a sense you can think of generalized entropies allow you to zoom into different regions of your scale-free distribution and magnify different aspects, either high-frequency words or low-frequency words. But I will go into detail. This is just an outline. And as a second part, I will mention some aspects discussed yesterday already, which is the notion of how we estimate these entropies or the variability in finite samples. And this is the notion that, I will skip that and just mention that for later. So information theory and divergence measures. So if we want to quantify the variability between two texts, we saw that the rank frequency distributions are essentially the same. So what we have to do is actually compare the distributions over words. And one very common way that is, or increasingly commonly used, is the so-called Jensen-Shannon divergence. And it basically just measures the Shannon entropy of the individual text. Or it's based on the Shannon entropy. And what you do is, in a sense, you just measure the entropy of the combined texts, where you combine the two texts. So it's an entropy of the average text, and you subtract the average entropy of the individual text. And why is that a nice measure? Well, you can show that this measure, actually the square root of this measure, it fulfills metric properties. So we can really, so it's non-negative, it is symmetric, and it even fulfills the triangle inequality. So we can really interpret this measure as a distance measure in a true sense, that these values that we measure, they have a true meaning. In addition, the information theoretic approach helps us in interpreting these measures. So in a sense, defining that this is not just a relative measure, it's saying this is large and this is small, but it actually, it helps us to associate an absolute value to that measure. And there's this nice paper which I really recommend to read, and they offer three intuitive interpretations of the Jensen-Shannon divergence, how you could make sense of that in terms of an absolute measure. I will focus here of this interpretation in terms of information theory, just to give you a notion what does it mean. And it, in a sense, you have two texts, and you assume that you close your eyes and you draw a random word from that text. So you draw some token. Then you look at you learn the identity of that word, and you ask the question, how much, learning the identity of that word, how much do you know from which of the two texts did it come from? And then this Jensen-Shannon divergence, it measures the average amount of information. Learning the identity of a word, do you know which text did it come from? And as an example, you could think of the word "the." It will probably have approximately the same frequency in both texts. So that does not help you to decide which text did it come from. So it's a very low information. Where a keyword, let's say quantum, it will have a very uneven distribution, very uneven frequencies between the two texts. So you will, once you find that word, you will be very sure that it came from that one text. So this gives you very high information. So this is what this measures, and it's, in that sense, we can really associate an absolute value in terms of bits that the Jensen-Shannon divergence measures. Building on that, so the normal Jensen-Shannon divergence is what has been used in many recent works, and the idea that we will propose, and I will show later why this is useful, is to generalize this measure by using generalized entropies. And what is a generalized entropy is, well, going from the normal Shannon entropy, we define an ensemble of measures. So which we index with a parameter alpha. Alpha can be any real number. So instead of having one value of entropy, we now have a whole set of values. And this is not our idea. Some people know this measure.
Is it not the Thales entropy?
So it is known in the physics literature. It is known as Thales entropy. However, as you see, this entropy has been proposed much before, and I'm not sure how that Thales, using this entropy, I think had something completely different in mind, which is not really related to what we're doing. So we're just using that measure. And one can use that entropy to define a generalized divergence measure. And basically there are, just to give one motivation why we use that particular generalization of entropy, there are many other ways to generalize entropy, any entropy, but the main advantage of this entropy is that it preserves these metric properties, at least for some region of values of this alpha, which the Rényi entropy does not, for example. So this is a main motivation to to keep interpreting our distance measure as a metric. And in the following, we will use and explore this divergence measure using this, basically not just having one single value of divergence, but having a whole set of values. And this is the end of the introduction. No, I forgot to mention OKS, which is another conceptual advantage is that this generalized divergence gives us a generalization of many heuristically proposed measures. And of course, for plugging in alpha equals 1, we recover our usual Shannon entropy or Jensen-Shannon divergence. But looking at alpha equals 0, we see that this will recover a measure that people propose as the Jacquard distance or a Jacquard index. Or if we go to the plug in alpha equals 2, this is something that people know as the Simpson index. So now we can know, basically having a generalized measure, we can see, plugging in different values generalizes different ad hoc proposed notion of.
Was there an interpretation of alpha based on additivity properties? Like this is a continuum of additivity, and alpha 1 means perfect additivity, no interactions between systems.
I think this is the Salis interpretation.
That's the Salis interpretation.
Yes. Yeah.
But when basically you have an alpha between 0 and 1, how you interpret that? I'm probably talking about that.
What is the exactly? This will be my next slide. Is to say what does it even measure? So perhaps I hope this will answer your question. So of course we want to know. We want to understand what does this divergence measure, which will come to my first major point. And for that, what do we actually measure with this divergence? And for that, I propose a very simple toy model. This is just for illustrative purposes. And we start from two identical distributions where we know the divergence is 0, just by construction. And then a very simple model of variability is just to delete one of the words, and then I create a new word with the same frequency. But it's a different symbol or a different word, right? So you could think in terms of language change. One word dies out completely, but we invent a new word which has exactly the same frequency. And then we can calculate, or plugging that in the Jensen-Shannon, when the generalized divergence measure, we will see that our divergence that we measure is the sum over all of these symbols that we replace raised to some power of alpha. So, and what does this mean, or why? Let's say where does this lead to? Is I will look at in the context of Zipf's law, is that I will consider two simple cases. Is I have a Zipf distribution, and now in the first case I will replace a word with a very high frequency, and in the second case I will replace many words with a very low frequency, and then I will calculate what is the what the generalized Jensen-Shannon divergence will be, what it will give me. And if I just look at the normal Jensen-Shannon divergence, which is alpha equals 1, what I will find is that both of these cases, which are completely different cases, right? In one case, it's the very high frequent word that changed. The other case is a lot of low frequency words that changed. They will both give me the exact same value. So I will not be able to distinguish these two cases. However, if I plot the generalized Jensen-Shannon divergence as a function, looking at it as a function of alpha, so I now go from -2 to 4, I will see that both of these curves, or both of these cases, will yield completely different curves. And just to lead you through this example is that the green curve is the case where I replace the low frequency words. I will actually only measure a substantial divergence for very small values of alpha. So choosing a value of alpha that is very, very small, I will amplify values that are in the tail, or a variability that is in the tail of that distribution. Whereas going to increasing the value of alpha in that spectrum, this divergence will not, it is basically 0, but what I will measure instead is the variability that I introduced from the symbol that I replaced with a very high frequency. So looking at the spectrum of these two curves, or these two curves, basically show that it's kind of a spectral information where I can zoom in and amplify at a certain region in the frequency spectrum. And just as an example, how this could, or yeah, this spectral information, just as it's a frequency, okay. But one example where this could be used, for example, is to distinguish the contribution of keywords or stop words. And here I compare two very large texts. One is 1 year from the Google Books, the Google Ngram database, and another is abstracts of physics papers. And I now look at two different sets of words. One is the 10 most common words, which is the, of, and end, which we could call stop words. And then I look at another set of words which are keywords from the physics categorization items, which are words like electron, engineering, gravitation. These are in total 300 words. And we see that they are located in different regions of the frequency spectrum. And now if I look at the contribution of only those two sets of words to the total Jensen-Shannon divergence, I will see that looking at the stop words in orange, the higher I choose alpha, the higher the contribution of those stop words. Whereas if I look at the keywords, there's an intermediate regime, which is where I see a peak in the contribution of those words. So I can, looking at varying this, the value of alpha, I can distinguish between the contribution of either keywords or stop words. So that's depending on what I want to measure. So there's no, let's say, best choice of alpha that I should choose, but depending on what I want to measure, I can here can obtain additional information. Exactly. And in that sense, I want to go to the second part, which is the second part we looked at with these divergences is how do we actually estimate those ones? Because every text is a finite text, so we always have only finite data. And the way we approach that is that we think of that in terms of a sampling process. So we have a distribution of words, and if we observe a text, we consider that as drawing n tokens from that distribution. And in that sense, I will never see the true underlying frequency. I will always have an estimator of that frequency, which is just the number of times I observe that word. Well, why do we estimate frequencies like that? Because if we have an ensemble of text, let's say we repeat that process many, many times, on average, I know that I will measure the true underlying frequency. Now, what happens with, in the end, I want to do the same thing for these entropies. I have a true underlying entropy, which it's clearly defined, it's a value I want to measure. And if I now want to estimate that entropy, I just estimate the frequency, plug it in my estimator, and I know there's a whole world of how to estimate entropies, and I will touch that later, but this is the most simple approach, and in this way we can do analytical calculations. And for everyone who wants to, I will show in 2 slides and touch that issue in more detail. But the issue with that, if we just use that plug-in estimator, is that you can show, you will, even if you repeat that experiment many, many, many times, you will never measure, you will never get to the true value of your entropy. So there will always be a bias. You will always underestimate the true value of the entropy.
So the bias is negative?
Hmm?
The bias is negative? Or?
Yes. Yes.
Okay.
The bias is negative. Yes. Okay. And of course, the same thing, since we use entropies to measure divergences, the same thing will be true for our generalized divergence. And you can, in addition to that systematic error, the bias, there's also a statistical error. And in the following, we calculated how this bias and how this statistical error, how it depends on the sample size n, how it depends on the parameter alpha, and in addition, I think that is the most interesting, guys, how it depends on the exponent in your Zipf's law, gamma. And this will have a crucial effect How do we do that? How large is the bias as a function of the sample size? So just to sketch, we'll just use our plug-in estimator. We'll make a Taylor series about the true frequencies. We can write down the first two terms, and after a little bit of math, we just see that the expected value of your divergence is the true divergence plus some term. And now I discuss this. It's a constant. There's one part of that term is 1 over n, which is 1 over the sample size, which is good because we know then going to infinity, that term should decay to 0. So that is good. And then there's this term V alpha. And what is this V alpha? This is a very you could think in the first approximation, that term is, or in previous calculations, that term is always assumed to be a constant as well. However, if we look at that term in detail, we actually see it's a generalized Heaps law. And how do we see that? And what it means is, if it's a generalized Heaps law, it means it has a non-trivial scaling as a function of the sample size. And I will show that if we use our usual alpha equals 1 case, the case that we normally consider is putting alpha equals 1, it's a 0, so it's just a sum over we just have to estimate our vocabulary. So we can calculate that very easily, as Eduardo basically already sketched. So we can calculate as this function, plug in the frequency distribution appears here, we can plug in Zipf's law, we get some very complicated function, but we know that this scales as our normal Heaps law with where the scaling exponent of our Heaps law enters. And we can repeat that in a very similar fashion, make that same argument for arbitrary values of alpha. We get some non-trivial relation as a function of the sample size of our alpha and our gamma, but as we will see that if we increase alpha above a certain value, our calculation shows that this term actually is not scaling as a function of n anymore, it's a constant. So there's a critical alpha above which this term will not show any scaling, and this will have some effect in terms of which alpha we will choose. So to summarize, we have this alpha. Putting in Zipf's law will give us a non-trivial scaling exponent. This is analytical calculations. To convince you that this is actually true in estimating entropies in the real context, we did some numerical simulations, basically starting from a fixed word frequency distribution, which we assume to be distributed according to Zipf's law. And now we just generate two texts, so of size n. One text from that distribution, another text from the same distribution. So we know the true distance between these two texts should be 0 because we generated them from the same text. It's trivial, right? But since those two things, they are of finite size, we will always measure the estimated distance in that case will always be finite. It's always larger than 0. And I will now show, first, just looking at the normal Jensen-Shannon divergence, the very simple case that people usually use. As a function of the text length, what is the bias that we measure? And for the case of an exponential distribution, where we don't have a power law exponent, we'll see that our bias decays as we expect. It's 1 over n decay. However, now if we sample our text from a power law distribution, we'll see that the bias is not only larger by a constant factor. What these results indicate is that the bias decays much, much slower. The scaling behavior is changed completely due to that power law exponent. So it means if we didn't know that, we would assume the error that we make in our estimation is basically negligible. But what this calculation indicates is that the error that we actually make is many orders of magnitude larger than what we would expect. And we cannot do anything about that whenever we have a power law distribution or a Zipf's law distribution and we want to estimate a divergence. And I want to stress that this is not related to the way or it's not conditioned on the fact we estimate, the way we estimate entropies. The way I estimated the entropies was this very simple plug-in estimator. We repeated the same experiment using different estimators that we found in the literature. So one is called Miller, one was proposed by Krasberger, and what I call the Bayesian estimator is this estimator by Neyman and the NSB estimator. And essentially having an exponential distribution independent of the particular estimator, we recover our 1 over n decay of the bias. Going to a power law distribution, we see for each estimator we will get the same decay, even though the Bayesian estimator seems, for very large databases, it seems to decay faster. But if we sample our text from an empirical distribution, we'll see that all of these estimators basically have the same performance. So there might be a constant shift in terms of one estimator is better by a factor of 2, but the general behavior that the decay is much, much smaller, we are not able to solve in that case. So these estimators are not able to address that problem. That raises the question, what happens if we now vary alpha? So this is the bias that we measured when using alpha equals 1. This was our predicted result. This is what we measured. And now we slowly increase the value of alpha. And you see that as I increase alpha, the bias decays much, much faster. Until a critical alpha is that critical alpha that we observe. So once we are above that critical alpha, which depends on my exponent in the Zipf's law, I will actually recover my original 1 over n scaling, which is what I want. This is the fastest decay that I can obtain, right? So that means I should, where's this, like how, the question is, how large should I make alpha in order to get that good decay? And I know that my Zipf's law exponent should be larger than 1. That means that the critical alpha, the largest critical alpha that I can see is alpha equals 2. So that means we can show basically that choosing the generalized divergence with a value of alpha equals 2 is the recovers our good scaling behavior of the bias. Having, or I'm formulating very bad, is we recover our expected 1 over n scaling of the bias for alpha equals 2, independent of the power law distribution in the data. So basically, instead of using the normal Jensen, what this suggests is, instead of choosing the normal Jensen-Shannon divergence, we should use the generalized Jensen-Shannon divergence with a value of alpha equals 2 in order to be robust with respect to bias or statistical errors. And if we did, so going to some examples, how is that important in real data? Is here I looked at the Google Ngram data and I compared the distributions of 1850 and 1900, and I measure the divergence between those 2 years as a function of alpha. And of course, since I'm increasing the value of alpha, I will amplify the differences between very common words. These words are very stable, means that the divergence in general decreases as I increase the value of alpha. These calculations that I showed you about the bias, you could say, well, the Google Ngram corpus is very, very large, right? So we have about 1 billion tokens. So we should expect, if we have a scaling that the bias decays for 1 billion tokens, bias should be sufficiently small. However, we estimated the bias that we make by bootstrapping our data, and we can actually see that using the normal Jensen-Shannon divergence, even for 1 billion tokens, our bias is still on the order of 10%. So even having these extremely large corpora, it's not clear that our estimator provides us a very good estimate of what we actually measure. And looking at these larger values of alpha, we can actually see only in choosing large values of alpha, this bias actually becomes negligible to the actual value that we're measuring. How's the evolution of the divergence over time? So how, in a sense, how fast does the vocabulary change over time? And what I measure here, or what I plot here, is I look at 2 years of the Google Ngram corpus separated by a time distance delta t, which I plot over on the x-axis. So I increase the separation in years between these two corpora. And choosing different values of alpha for all of these curves, I see that the divergence increases over time. Yeah, so which is clear, it's what we expect. However, what we see here, choosing very low values of alpha is 0.0, 0.5, or 1, means that as we go to delta t equals 0, it seems that the divergence that we measure is not decaying to 0. Yeah? Because as delta t goes to 0, this divergence should go to 0 too, because the two corpora are from the same year. So only for alpha equals 2, this divergence actually seems to converge also to a value of 0. So this means that this is this finite size effect for delta t going to 0, which is an artifact of that bias that we will always measure. Curiously, for which we don't have an explanation, is there's a time dependence of the divergence as delta t squared, which you can see if I plot the square root of the divergence as a function of delta t. And it means that the rare words, they change faster. Rare words, very small value of alpha, and the frequent words, which I measure for larger values of alpha, change much, much slower. So we are not sure how to interpret that, or we're not completely sure. If you have ideas, I'm happy to discuss that. So this is one application. Another application where we recently applied to actually show that this measure of using the robust measure, the generalized Jensen-Shelmian divergence with alpha equals 2, is actually useful, is an application of, and it's a very recent result, about the evolution of scientific disciplines. And we were able to obtain about 10 million articles from the Web of Science, and they are categorized into different fields, we call it fields. So this is natural science and then mathematics. But what we do is we take, for each field, we collect all our scientific papers, we collect the text, and we can...
The abstract.
Yes, it's the abstract, sorry. Yes, I have to clarify. These are very short texts, but for each of the scientific fields, we collect many, many abstracts. So we obtain, for each individual field, we obtain a word frequency distribution. And now we calculate the textual difference, the textual distance between the scientific fields based on our d alpha equals 2 measure that we previously showed to be the most robust estimator. And we can now follow this over time. How? So here I plot an example of physical sciences versus chemical science, and we see that the earliest year we have data is 1991, to the last year is 2013, and for those two, there's many disciplines for which there's no trend that we can actually see. So physics and math, or physics and chemistry, it's very constant over time. However, there's individual cases looking at physics versus electrical engineering, is that the distance is actually increasing over time. So these two fields seem to be, language now, this analysis allows us to show these two fields seem to diverge, at least in the words that they are starting to use. Other examples which are interesting is comparing physics and biology, or physics and computer science, which from this analysis seems to be converging to. And one can do a more systematic analysis by looking at what is, for every pair of fields, what is the average, are they on average converging to each other, or are they diverging from each other? So what is the change in their relation? And here we looked at particular cases of the case of computer science, how it changes with respect to all the other fields that are present in our data set. So each black dot means how does that discipline or that field change with respect to computer science. And if that value is smaller than 0, it means these two fields are becoming, or these fields are becoming closer to computer science. And on this plot, we see that actually almost all the fields that we see in our data set are becoming closer to computer science. And some examples include especially biological sciences or physical sciences, and there's other sciences which are not included in that general trend. But what this suggests is that computer science is becoming closer to basically every other discipline that we can measure. So it's indicative of showing that there's a tendency that this is becoming a more central discipline, which is consistent with what we observe at least to my experience, seeing that many disciplines are starting to use methods from computer science. And we're able to see that just from the language data. There are other cases, for example, just to see that it's not a general tendency that everything is becoming closer. Other cases like chemical sciences is on average staying constant or not changing. There's some fields for which they diverge, some fields for which they diverge. And then there's something like psychology which seems to diverge from, it's doing its own thing. So this raises the, but that's interesting. So it seems there is...
Psychology or cognitive science?
Mathematics, okay.
Okay.
But, and in that sense, it allows us, it's a different or a complementary approach to measuring relation of scientific fields to what is usually done in terms of citations. It offers a new view, and especially this terms of the overlap of language that is used is interesting in the question of interdisciplinarity that is usually answered. Is interdisciplinarity good or bad? And here we see that there's some disciplines which seem to combine or are a bridge between disciplines. For some disciplines, this does not seem to be the case. But in general, it is usually claimed that interdisciplinarity is increasing. And in a sense, a final result that I want to show is that on the general scale, it is very, at least looking in terms of languages, is very hard to claim something like that. So here is now comparing all pairs of fields, and we measure whether they are converging or diverging over time. And we plot this histogram of values that change, and there's some pairs for which they diverge, some pairs for which they converge, but on average, it's very close to 0. You can make a hypothesis test, and to test whether the mean value of that is consistent with having no change at all, and this is what we find. We're not able to reject the hypothesis that the mean value of that distribution is 0, which means on average, these tendencies of, let's say, separation or diverging and tendencies for convergence, they're in balance. So
but isn't it some mathematical fact?
No, because this measure is an absolute value. It's not a relative comparison.
Exactly.
So you could have all of them converging or all of them diverging.
Oh,
exactly. Yeah.
That's
It's not
the advantage of this measure.
Yeah. Exactly. So this is just one example to show it's useful, and we can look at new things. And from that, I want to conclude is one thing I hopefully could say that these generalized entropies are useful to look at this coexistence of universal aspects of language and the variability. That these two things are not independent, and it's a very intricate relationship between those two things. And one of those things is that we can actually, it's not just saying the variability is, or the distance is 0.5. No, it's more complicated than that, or we can do more. We can say, for frequent words, it's actually more stable. For not so frequent words, it's much less or much more variable. And the third aspect is that all these things is this dependence on sample size, and this is non-trivial because of the heavy-tailed nature of this Zipf's law. And even if you use state-of-the-art entropy estimators, it is very hard to get rid of these problems of convergence. And using these generalized entropies, it is one way to get rid of that problem, to use a different value of alpha. this is, let's say, this is our solution to do it because there's this problem exists. And with that, I want to conclude. These works are, yeah, that's it.
Thank you so much.
So when you show this scaling,
Yes.
that the divergence scales as the square of the time difference, right?
Yes.
So if you put in a simple diffusion process or something like a Markovian process, do you know how it would scale? So is it different than a simple diffusion or simple random Markovian process? Or is there a drift term in this?
I mean, what would be the Markovian process? Because it's kind. It means here it's word frequencies are slowly changing over time, right? And then it's that slow change leads to a delta t behavior. I'm puzzled. I don't know how to have a simple explanation for that. I'm not sure if I have a good answer for
Can you
this question.
say what is diffusion process here?
Yes, so for example, you have a transition matrix specifying which word is changed to each other with what probability. So
We would have to do that. Yeah, I don't know. I don't know if that would lead to something.
Just a remark. So the square root is the distance, right? So the distance is growing linearly. So I don't think this is so surprising. So it is. I mean, the linear form is just saying that the distance grows with time linearly, right? So why these values and what is a model that explains that, we don't know. But it is, the distance is linear in time, and it will be interesting to have a model that generates this, but it's not so easy because there are millions of words, what are the transitions and so on, right?
Yes.
Okay. So it was such an interesting observation with this behavior of basis of shift in heavy tail distributions.
Yes.
But there was you knew theoretically that it should happen, and you simply showed us, or it was just experimental discovery?
No, I showed these numerical simulations because
But did you know?
One part was the analytical derivation, and there's a lot of assumptions that I make about during the analytical derivation, which I don't know if that is true once I do the numerical simulation, or if that happens in real data too. Because I do a Taylor expansion and I cut off after 2 terms, so I'm simplifying the problem a lot. It's not clear that this simplification yields an answer that describes the data or the sampling process that I do. In that sense, it was a confirmation of the analytical results that we showed.
Analytical result predicted that it will decrease slowly or not?
Yes.
The alpha 1 case was done in the 90s, right? So the Jensen-Shannon was done in the 90s. The contribution is to expand this for different values of alpha.
Okay. Damien?
Yeah, thanks. So then let me see if I understood correctly. One of the big motivations of introducing this generalized entropies is because you can reduce the bias, which is an extremely important thing. You can actually get something that approximates statistically you want to see, right? And then you found that a large value of alpha leads to a smaller bias, which also means that you're going to be putting all of the weight in high frequency words, which, if I have to make a pessimistic view, is like, forget about saying anything on language change for low frequency words, right?
Yes, it's that trade-off that you have to do. It's like, if I want to look at, or if I put more emphasis on the high frequency words, I can trust the result more. If I want to look at less frequent words, the calculations show that this result is less reliable, much less reliable. This is then the trade-off that you have to do.
That makes sense.
Yeah, it makes sense. Yeah.
No, it's very interesting. So you were mentioning Bigman's work, and one of the things he's doing right now, I think, is he's counting the number of new terms in subsequent years. So they're actually putting all of the effort on language change on low frequency elements. But your results suggest that
I mean, the results.
Exactly right.
The results that we suggest here is that even for delta t equals 0, you will measure a change, right? How meaningful is that? Like if you would extrapolate that to, because this is delta t equals 1, could extrapolate to delta t equals 0, then you would measure something that is on the order of, I don't know, this is 10, this is 20%. So this is an artifact, right? We know it's not real. So in that sense, one would have to address these issues. We know that they exist. Yeah.
Okay, what?
Just probably a very, very simplistic question, but in relation to your rare words changing faster, frequent words changing slower.
Yes.
Is that just a result of frequent words being very short and rare words being long? Because if you look over the primate sort of tree, the vocalizations are made most frequently are very, very short, and they're conserved over the tree. Because there's nothing really to change within them.
So here, yes. So here I'm only looking not in a change in the meaning. I'm not able to resolve that. What I'm only resolving is for a fixed word, how that frequency changes, how the usage, how the frequency of usage, how often that word is used. It's not how the word, if a word is getting shorter or longer. It's only but it's I didn't clarify that. I should. But it's only a fixed word form. How this word form changes in frequency of usage. Yes. Thank you.
Yeah, I wanted to make a comment. I'm very glad to see that you see less variation in high frequency words.
Yes.
Because I think this is theoretically helpful for those who try to claim that there is some optimization in language. Because a priori would say, well, is language far from equilibrium or not? You would say, oh, there are words coming in, words coming out, but there seems to be a core that is more or less stable, in which optimization could easily operate, right? So that solves an old puzzle of some physicists telling me, how do you believe in optimization in language? Because the system is out of equilibrium and therefore we shouldn't expect the dynamics being driven by minimization of some cost function. Yeah? So I think that it goes in that direction. I see you agreeing. That makes me happy.
Yeah, I totally agree. To comment on that, I mean, it's a bit misleading maybe to put these curves in the same plot, right? This is several orders of magnitude slower, right? So this is on the order of 10 to the 1, this is 10 to the 3, 10 to the minus 3. So the change there is really much slower. It's very, very constant.
And I think from a linguistic point, it makes sense that high frequency words change slowly, right?
Well, but in this case, you're not really talking about changing the word in terms of changing the sounds, but replacing them, right?
Yeah.
And
no,
if you think
about
about
in frequency, right? Yeah. Capturing variation in frequency in the high frequency domain.
Well, I mean, it's if you think about a kind of S-shaped curve of replacement, then you have one word which comes in, has low frequency, and then kind of pushes another word out, right? And I think it makes sense. You know, it has higher probability that you replace Rechner in German by computer than to replace für by for, right? Yeah. So in terms of borrowability of words, and also in terms of neologisms, it makes more sense that you replace infrequent words by either words from other languages or by Latin words than stop words.
There was also this work on regularization of verbs. Also, that was.
I thought of that.
It is also in the same spirit.
Yeah, exactly.
Yeah, I mean, first I thought of Mark Pagel's work on how frequent words actually reflect deeper past, but that's more about the change within the word, right? So they don't change, the sound change is slower for frequent words, but that's not necessarily what you observe here. It's about the frequency, right?
Yeah. It was more about replacement, right?
Yeah.
In the case of Pagel, it's whether a given word enters or leaves the vocabulary.
Yeah.
Mm-hmm.
I thought it's about. Yeah, I'm not sure.
Another question. It's a small technical question, but when you did the applications, did you remove the bias?
No, we did no. In you mean in this case here?
Oh,
No, here
you
we
showed
just
different
measured. Yeah.
applications.
Yes. We did not replace the bias. Our solution to the problem was using this estimator of alpha equals 2, where we show that if we have a large sample size, this bias
so
will be orders of magnitude
Okay, so you presume
smaller.
the bias.
Yes, this was our motivation to.
Okay.
In the end, telling the story differently is we started with applications.
Okay.
Didn't trust the results that we got because we discovered all these dependencies on sample size, which in a sense led to this starting to investigate what are we actually measuring, and then we found all these things. So that in a sense,
That was
I'm telling it now the other way around,
Yeah.
but how we started that project was actually motivated by having applications and not really understanding what is it that.
Okay, thank you for the clarification.
Yes.
Any other questions?